And it's quite general term, in fact. So if you have some data to analyze, then one thing you typically do is to, for example, it is some kind of a spatial structure like this in two-dimensional space. And this two-point correlation function usually consider that how this point Ri and how this point Rj are related. Of course, this terminology related can be very subjective, so we need some clear mathematical definition of them. So, for example, this correlation can mean that in population, as we already mentioned, this correlation refers to the probability that these 2 points belong to the same connected cluster or something. And if this is a more physically meaningful object like the potential landscape, then maybe these two, the correlation function between these 2 points can refer to the relative difference in the, for example, the electrical potential in this landscape. But in the Ising model, it has a very clear meaning. And perhaps it's easier to understand by explicitly writing down this form of the correlation length, like this average S1 and Sj minus average of Sj. To really careful about this average term. So it means that this part is deviation of the spin variable from the average value. And the same for the Sj. It's deviation of Sj variable from average of Sj. So each of these terms in this product refers to the deviation itself. So this actually represents so for example, I will denote this Si as a red color and Sj as a blue color. Then suppose we have this average value of Si is here, and Si can be here or anywhere. And for example, this average value of Sj is here, and the real Sj can be anywhere. So this deviation can be positive or negative, or largely positive or hugely negative. And the concept that suppose these two variables, Si and Sj, are completely uncorrelated, then the fact that Si is above here or below here does not affect the direction of this deviation here at all. So if you average out this product, so sometimes it goes the same direction and sometimes it goes the opposite direction. So if we average out this term, it will close to zero when these two variables are completely uncorrelated. But suppose these two variables are really closely correlated, then the fact that this Si is higher than the average value make the probability that Sj is also higher than its average. It will increase the probability of this. The same for the negative part. So if you consider this as some temporal notion that in at t is equal to 1, it deviates above direction, and at the next time t is equal to 2, this deviation is toward the negative side. Then there's a because this is a strongly, if these two variables are strongly correlated, the direction would be the same. Maybe of course it's possible to have a different direction, but the fact that if we assume that these two variables are highly correlated, they tend to move together. That is the most important part. So the notion is that if these two variables are tends to move together, this correlation function would be positive. Of course, the other way can be possible because if these two variables are anti-correlated, that means that if this SI variable goes up, there's a higher chance that this SJ variable goes down instead of goes up. And of course, the uncorrelated part can be represented by if this is close to 0, it means that this SJ does not care about this situation of SI at all. So that's why we call this as a correlation length. And if you digest this concept clearly and look at this Ising model problem again, then you now get some idea. If two spin variables are moving together or in a very highly correlated way, this value could be larger than 0, and maybe it's even very close to 1 actually. If these two variables are completely moving to the completely same direction all the time, then this one can be very large value. But because of this restriction, it cannot be higher than 1, but anyway, the maximum value can be 1. It's a slightly tangent here, but this kind of correlation function is introduced a lot, especially for like other contexts like temporal data. So if we compare the totally off topic, but suppose you have some data like this, it means that this data, the data points at this time and this time is similar, but this one and this one can be very different. If this is a temporal direction, we actually calculate this correlation between these data points at t0 and t equal to tau. So it's a correlation to itself, but at different time. And because this deals with the same data, but with a different time, we usually call this autocorrelation. So here auto means there's a correlation to itself, but in the different times. So by measuring this autocorrelation, by increasing this tau, then we have how longer or how long is the typical scale of the temporal variation of this data, which is this is a completely data science part, but anyway, so it's kind of similar topic. But here in the Ising model, instead of dealing with the temporal side, we deal with this 2-point spatial correlation. And so we are dealing with the space here. So suppose you have these two pair, and these two pair 1 and pair 2. So which of these two pairs are more correlated to each other in the Ising model? Yeah, it's a simple question because the fact that these two spins are close together means that there are higher chance that these two spins are moving together. Actually, maybe in some extreme cases they are actually adjacent to each other, so that has a directly interact with each other. For these very distant spin pairs can be correlated, there must be some very long range ordering process here. And in many cases, they are likely that they are not correlated. So this is the concept, the very important concept of the correlation length in the spin system. So it's a little bit more subtle than just a simpler problem of the population. So in that case, it was much easier to understand because that was just defined as simply the probability that two points or two sites in the population problem belong to the same cluster. But this is a little more subtle one. But anyway, this is defined. The correlation length in the Ising model is usually defined like this. But let's recast this formula here. So as you know, this is we can just expand this inside this large average, the outside average thing. So it's a SI SJ and minus SI average times SJ and minus SI times SJ average and plus SI times SJ. So average over this. Then we have SI SJ average and because this part is already averaged out, so it goes outside of this average, so it's minus SI. And the only thing remains is the average of SJ, so it's same thing for this one and plus. So this will cancel out, so we end up with much better expression. It's like this. So instead of just taking the deviation of individual spin, we can just take the average of this product and the product of the average. So it's a kind of also rhythmical way to remember this correlation. So for example, if SI SJ is the same as the product of these two, then of course this correlation function is 0 because this is the definition of this correlation function. And it's intuitively understandable because this formula means that the average of the products is the same as the product of the average. It's a typical intuitive notion of an uncorrelated variable, the property of the uncorrelated variable. So it totally makes sense. So now let's combine these two things. Then what kind of identity we will get? So first, let's starting from this fluctuation relation, this one. And if you recall that this magnetisation is actually Let's denote this as a K. So this is a definition of the capital M. It's a capital M because it is not divided by N yet. So it's just M. So it's square of this one and here. As you know, these two are clearly different, of course. And of course, one thing you can do is that intentionally, let's just this square as first using this index K and using this index J. Maybe you are getting the impression that we are writing down this simple expression into more complicated part. And of course, this K and J are the dummy variables, so it doesn't really matter. So it's always we can always do that. And of course, instead of using this, let's write down this as again, seemingly kind of silly way. And again, the fact that whether we use this variable K or J or X or whatever doesn't really matter because this is just a summation index. Then, in fact, now we realize that all of these terms are just a summation over K and J index. So we can simply write down this as a, so make this completely out of this averaging process, etc. And it's possible because this averaging operation is completely the linear. So we can actually sk sj minus sk and sj. Perhaps this is the most abrupt change, but if you think about this deeply, it's not hard to see these two expressions are equivalent to each other. It's easier for you to derive from here to here, but yeah, it's not hard to see that these two are identical to each other. But in fact, we already learned what this is. This is the correlation function or correlation length, but the only difference is that instead of using this I index, we use the K index here. So this is the correlation length between site K and site J. So basically, this NKBT times susceptibility chi is the same as the sum over correlation function for every possible spin pairs. But one thing is that because these summation are unrestricted sum, we can actually write down this as I will just write down the answer and explain to you. This, so I is a kind of an arbitrary location. But because of this unrestricted term and the periodic boundary condition is possible when it's applied. So somehow in the very large size limit, we can actually convert this double summation as a single summation times n, because as we did for the beta lattice or infinite size system in calculation, when we deal with this infinite size system, all of these, each of these sides can be equivalent to each other. So we just fix first spin and sum over all the correlation function for all the other sides, and just times n will be the equivalent to each other. It's kind of hard to say here, but I put the explanation here. So the fact that suppose we are dealing with some translational invariance system, meaning that if you move each side by in parallel transformation, so if you multiply this like this with for any vector, so it's a transformation. So the relative distance between these two are the same, just by adding this vector, arbitrary vector r. So it doesn't really matter whether we calculate this centered at Ri or any other side. So due to this translation invariance, we can just take a single reference point, Ri, and sum over all the other spins and make this n times bigger than this. So, so in this case, this would be the equivalent to this case. It's kind of hard to grasp at first, perhaps. So this invariance is invariance. So for example, GRK and GRJ and GRK plus R. The important part is that adding this the same vector. So it's easier to draw this. So for example, in the two-dimensional system, as an example, instead of this correlation between Rk and Rj, what's the role of this translational vector R? So we can actually, instead of calculating this, I should not move this. So instead of do this, we can just move it around like this. So all of these, if we choose R arbitrarily, we can have this transformation of this one or whatever. But the important thing is that suppose we have this one plus R, then this transformation would be simply plus R, and also this parallel transformation. And the question is whether correlation between these two and between these two are the same. Of course, in general, it can be different, but as I already mentioned, when we are dealing with the very large system size or even the periodic boundary condition or the thermodynamic limit where n goes to infinity, then these should be the same. This could be a big assumption, but it's quite relevant for most of the large system. So with this argument, we can replace this double summation as a single summation times n. Yeah. You can think about it. to fully understand what this means. And then the final step is to take this summation as, by taking the continuum limit, we can actually convert this to integration. So of course, when we deal with the integration, we have to put some kind of volume variable here, or the length scale variable in the denominator to make all this as a dimensionless. But in our textbook, we actually skip that part. So by do that, the sum or integration of this correlation function over all the possible spin system is just the KBT times susceptibility. So this is a relationship between correlation function and the susceptibility. That is what this means here. So again, this relates the spin-spin correlation function to the free energy per spin with the susceptibility. So if you recall, in the first semester, when we deal with the percolation problem, this corresponds to the fact that sum of the correlation function is the same as the average cluster size or something. In that case, that would make much more sense. But here, it's less physically intuitive, but mathematically they are equivalent. So that's why it's possible. So some of the so it's kind of a rule of thumb that maybe you can remember that this formula is a sum of correlation function for every different sites would be the same as the susceptibility. So again, basically it's from this concept, the fluctuation dissipation theory. Non-interacting spin, the energy is just negative of h over si. So it's essentially this one. So, and of course, this one is, we can take the average energy, I believe. So the average energy would something like this, and this one become this, and this is a minus hn hyperbolic tangent theta h. So the epsilon, or the average energy per spin, is negative h hyperbolic tangent beta h. This is really simple. So this average energy is directly proportional to magnetization in the case of the non-interacting spin. But for interacting spin, or the genuine Ising model, it's not possible to have this simple thing, because now we have to calculate this one. So the average of this energy is no longer just a proportional to this minus h. So even if we can calculate this part, it's not sufficient to calculate this average energy because we still have this highly non-trivial term. So even if we have this one, to calculate this, we have to actually calculate this from this partition function again. So the mathematical derivation is not that difficult, but the one thing I would like to point out is the fact that this clear difference between these. For the non-interacting spin, it's basically each spin here contributes +1 for magnetization and -h for energy without consideration of any other spin variable. But for this case, the fact that each spin is upward means that +1 for magnetization. But can we decide the energy contribution from this spin alone? That is the question. So here, the bottom line is that a single spin up or down determine both the magnetization and the energetic contribution. But for this interacting spin, the fact that one of the spin is aligned upward means that, of course, it contributes +1 amount to the magnetization. But without the knowledge about other spins, we actually cannot determine whether this one increase the energy or decrease the energy. So if this neighboring spin is in this direction, then this upward direction would decrease the energy. But suppose the other spins are going downward, then the existence of this upward spin actually increase the energy. So that is a very crucial difference between these two situations. So that is the reason why for the non-interacting spin, we don't need to calculate energy or average energy separately even. But for this case, because of this non-trivial term, it's not just a simple proportional relation. So we have to actually calculate this with this standard formula, even learned earlier in the undergraduate statistical physics course.